Welcome back to our podcast where we dive deep into the fascinating world of data processing. Today, we're exploring the evolution of batch processing beyond the traditional Mapreduce model. We'll discuss how modern systems are designed to optimize resource utilization, improve efficiency, and handle complex workflows. So, grab your headphones and let's get started. To kick things off, let's set the stage by understanding the core concept of Mapreduce. At its heart, Mapreduce is a programming model created for processing large datasets across distributed systems. It separates tasks into two main functions, mapping and reducing. While this model has been revolutionary, it does come with its own set of challenges, particularly regarding resource allocation and job execution. One key aspect of Mapreduce is its architecture, which allows for non-production tasks to be overcommitted. This means that lower priority jobs can utilize resources that might otherwise be idle. However, there's a catch. These jobs can be preempted at any time if a higher priority process needs those resources. For instance, at Google, a Mapreduce job running for an hour has about a 5% chance of being terminated to accommodate a more critical task. This preemption rate is significantly higher than failures caused by hardware issues, which means that jobs often need to be designed with this uncertainty in mind. Now, while Mapreduce is robust and can handle large quantities of data, it's not always the most efficient choice. As we move into the realm of open-source cluster schedulers, we notice that preemption isn't as widely adopted. Systems like Yarn and Kubernetes lack general priority preemption, leading to inefficiencies in environments where task termination is less common. This raises an important question. If Mapreduce isn't the best fit for every scenario, what alternatives exist? As we look for alternatives, higher-level programming models like Pig, Hive, Cascading, and Crunch have emerged to simplify the complexities of using raw Mapreduce APIs. These tools provide abstractions that make common batch processing tasks much easier to implement. However, they don't necessarily address the underlying performance issues that can arise with Mapreduce. One significant limitation of Mapreduce is that every job is independent. If you want to chain jobs together, you must manually set up input and output directories, often requiring external workflow schedulers. This can lead to inefficiencies, especially in complex workflows where intermediate states need to be materialized, essentially writing out data to files before it can be used in subsequent jobs. This brings us to a critical comparison with Unix pipes, which allow for streaming data between processes without the need for full materialization. In a Mapreduce setup, jobs must wait for all tasks in a previous job to complete before starting, which can slow down the entire workflow. Additionally, mappers often redundantly read files that were just written by reducers, leading to unnecessary overhead. So what's the solution? Enter modern distributed batch computation systems like Spark, Tez, and Flink. These systems are designed to handle entire workflows as single jobs rather than breaking them into independent subjobs. They utilize a data flow engine approach, allowing for greater flexibility in how tasks are connected and executed. One standout feature of these newer systems is that they only perform expensive operations like sorting when absolutely necessary. This is a significant improvement over Mapreduce, where sorting occurs by default between every map and reduce stage. Moreover, these systems can start executing operators as soon as their input is ready, eliminating the delays that come from waiting for entire stages to finish. Another advantage of these data flow engines is how they manage intermediate states. Instead of writing data to a distributed file system, they can keep intermediate states in memory or on local disk, reducing I/O overhead. This means that tasks can execute more quickly and efficiently, leading to faster overall processing times. Now, let's touch on fault tolerance. In Mapreduce, fault tolerance is relatively straightforward because tasks can simply restart on another machine using the same input from the file system. However, systems like Spark and Flink employ a different strategy. They recompute lost intermediate states from available data, which can be more efficient in many scenarios. As we wrap up this exploration of modern batch processing, it's clear that while Mapreduce laid the groundwork for distributed data processing, newer frameworks have emerged to address its limitations. By optimizing resource utilization, reducing unnecessary overhead, and improving fault tolerance, these systems are paving the way for more efficient data workflows. In conclusion, the world of batch processing is evolving, and understanding these advancements is crucial for anyone working with large data sets. As we continue to explore the landscape of data processing, we'll see how these innovations not only enhance efficiency, but also open up new possibilities for data analysis and application development. Thanks for tuning in today. Be sure to join us next time as we delve into the exciting realm of stream processing and how it complements batch processing. Until then, keep exploring the data-driven world around you.